So this is going to be a short video looking at the dissolving process at the molecular level, gauged to an introductory level chemistry class. So dissolution at the molecular level, dissolution just means the process to dissolve. Whenever you have the concept of dissolving, you have to decide what the solvent is and what the solute is. The solvent and the solute determination has nothing to do with solid, liquid, or a gas. It's only to do with the magnitude of the material. So for example, if you have a mixture, which member of the mixture is the solvent and the solute? The solute by definition is everything other than the solvent, and the solvent by definition is the one thing that's in the most abundance, whether it be a solid, liquid, or a gas. Okay, so let's consider just one solute and one solvent. And we'll consider the solvent water. So I'm going to draw some spheres close to each other. There's some gaps, but pretty close to each other. And I've got 4, 5, I'm going to have 8 spheres. And this will represent our solvent, where a sphere is equal to a water molecule. So a sphere here is equal to a water molecule. L just means liquid. Again, it's not a solvent because it's a liquid. It's a solvent because there's going to be more water molecules than anything else. I'm now going to consider, and I'll do it in black as well, but I'll do it in solids. I'll consider that we have a solute. I'm going to make the solute a solid. I'll just do 6 colored circles. And I'll say that this is the solute. And here the colored circle is, I don't know, let's say it is, let's say it's glucose. Glucose, we can write C6H12O6, that's the formula for glucose. And let's say it's a solid. Again, it's not a solute because it's a solid, but there's just going to be fewer of them. And I don't necessarily mean the fact that the 6 spheres is fewer than 8 spheres. I just mean that if I looked at all of the water molecules, there'd be a lot more of them. And if I looked at all of the glucose molecules, there'd be a lot fewer of them. Okay, so I have my solute and my solvent. Now, what's going to happen is I'm going to form a solution. Another name for a solution is a homogeneous mixture. But for this to happen, I've got to convince the solvent molecules to stop interacting with each other. So if you look at my video on intermolecular forces, you'll see that water molecules will interact with each other, and to break those interactions costs energy. Likewise, glucose will interact with its nearest neighbor. I've got to convince the solute to pay less attention to itself and start to pay attention to the solvent molecule. So what's going to have to happen is we need to add energy. So I'm going to say add energy, so plus E. I've got to add energy to separate these out a little bit. So I'm just going to redraw them, but with larger gaps between them now. So basically separated them all out. I've broke their interactions, or I've at least weakened their interactions. Likewise, we've added some energy. Where did that energy go? It paid the price of breaking these guys up. Okay, so it took energy to do that. And in general, it always takes energy to break something. Consider a window, for example. If you want to break a window, which I don't condone, you would have to throw energy at the window in the form of mass. it costs energy to break anything. Break a twig, it costs energy. If you break interactions, it likewise costs energy. So that was an energy cost, but now we're able to form another interaction, and it might be with our neighbor again, but also we've got the chance of persuading the material to interact with something else. So they can come together now. It's going to take me a few seconds to draw this, but I'm now going to 8, 9, 10, 11. So let's see, I've got 8, 9, 10, 11, 12. Okay, so I've got an equal number of spheres, and I know 6 of them are going to be colored. So I'll try and evenly distribute 6 of them. And 8 of them are not sphered. So let's say this is our solution. And a solution we'll say is aqueous. So it's really a glucose solution, right? So rather than put the label aqueous here, I should probably put it here. So we've got our aqueous solution. This is also called a homogeneous mixture. Where we know here that homo means the same, genus means type, so this is a mixture of it's a mixture of 2 or more types of matter, where to the unaided human eye, everything looks the same. Okay. The collection in the solution, so what's the energy change here? When these materials came together to form this collection, there was a collision of materials. The solvent molecules were attracted to the solute molecules. There was interaction. There was, I don't want to use the word grinding, but there was a grinding together. Hypothetically, they didn't really grind. But there's the proverbial grinding together of bits and pieces. And we formed this homogeneous mixture. Well, just like the collision of any objects, your hands, 2 metal rods, anything that collides releases energy. So this will be a release of energy. Release is another word for loss. There's a loss of energy from this system out into the surrounding, and we can measure the surrounding. So essentially, if I were to measure this bit, this would be, I'm going to call this a hot step. I'd know it was hot because if I measured its temperature would go up. And conversely, these are cold steps. If I measured these, the temperature would go down. So I'm saying hot and cold just for simplicity. It costs energy. The surrounding pays for that energy, so the surrounding gets colder. This releases energy, the surrounding benefits from that release of energy, so the surrounding gets hotter, and we can measure that with a temperature, with a thermometer. Okay, but we have to remember that this whole process is one process. So let's call essentially we have the cold steps, let's call the cold steps A. So that's A, and this is also A. And this hot step, let's call it B, where A and B are just different labels. So we have overall, we have the total energy, or the change in the total energy, is going to be the sum of A plus A plus B. Okay, so we've got to add all of these energy steps up to look at the dissolution process overall. Remember, and I'll put these in parentheses, this is the cold step, and this is the hot step. Well, a couple of things can happen. Numerically, so these are energy values that can be calculated. If A is greater than B, overall it would be a cold process. So what does that mean? This means something like an ice pack. So if you dissolve a solute in a solvent and overall it's a cold process, that means the temperature of the dissolution process would be to decrease. So this will get cold like an ice pack. So whenever you've mixed chemicals together and it gets cold, or literally if you go to the store, well, back when we were allowed to go to the store, because I'm recording this video during the COVID-19 pandemic. So back when it was a bit easier to go to the store, you could buy ice packs and you shake them and they get cold. This is what's happening. If A is less than B, it would be a hot process. This would be a heat pack. So likewise, when you go to an outdoor type of store, you can buy those hand warmers, that little pouch that you shake, you put in your gloves, and it gets warm. This is essentially what's happening. You shake it to mechanically mix a solvent and a solute. You have A processes and B processes, and on that occasion, B is larger than A, so on average, the whole thing gets hot. And we register that as a raise in temperature. Okay, so this, in a nutshell, is dissolution at the molecular level. Treat it as a three-step process where you've got breaking apart of intermolecular forces within the solvent, breaking apart of intermolecular forces in the solute, recombination of solute and solvent, and then you look at individual energy contributions. But what you observe in the real world at the macroscopic scale is an averaging of all of those effects. I now want to spend a few minutes looking at the role that concentration has on solubility. Okay, so we've just seen dissolution at the molecular level. Let's consider a gas. So consider a gas, and actually let's consider an ideal gas. So if you look at my video on ideal gases, you'll see that an ideal gas just means relatively low temperature and pressure. Not too low, but not too high, because then it would be real. So real gases are the extremes of temperature and pressure. Ideal gases are in the middle. So an ideal gas, for example, would be the gas in a typical room that you're sitting in right now. And I can use the ideal gas equation. So I can use PV is nRT, where P is pressure, V is volume, N is moles, R is the ideal gas constant, and T is temperature in units of Kelvin. If I manipulate this equation a little bit, I'm basically going to divide both sides by V. So let's divide through by V. So we have P is N over V RT. Okay, so we have this manipulated form of the ideal gas equation. And let's look at this object in brackets here. So N over V, well, that's moles per unit volume. Well, if we insist that the volume is in units of liter, and moles obviously is just moles, that's the unit of mole, then this is molarity, which has the symbol capital M. And molarity just means concentration. So moles of what? Moles of solute. Volume of what? Volume of solution. So as long as we're talking about those things, then we have molarity, and molarity is concentration. So this is a way that we can quantify the dissolution process. So we know how the dissolution process happens at an early introductory level. We can now quantify to what extent as the dissolution process occurred. Notice that we have a fraction, and notice that both the numerator and denominator have a unit. So whenever the numerator and denominator of a fraction have a unit, we have an intensive property. So molarity is an intensive property and that means it's independent of sample size. This means it's a constant. This means it's a very valuable property. And we need to know how to calculate molarity. And for my students, I've posted some examples where we do just that. So molarity is something important we need to calculate. And I've got it right in my ideal gas equation. So because it's given the symbol capital M, let's rewrite this as pressure is concentration, molarity capital M, RT. And now we're starting to see, if you look at my video on colligative properties, we're starting to see the emergence of something that looks like osmotic pressure. If we relabel P as pi, the Greek letter for P, then we'd have pi is MRT, and this is more like the form of the equation for osmotic pressure. Okay. If we ignore these constants, so let's say at a fixed temperature then becomes constant. The ideal gas constant is a constant. So let's just remove the equal sign, ignore the constants, and look at proportionality. We've learned that pressure for a gas, we're still talking about a gas, is proportional to concentration. So we know that the concentration of a dissolved species is proportional to its pressure. So we can use a common example here. Think of soda. If I want to increase the carbonation level in my soda, I'd have to increase the pressure of the carbonation process. So if I want to have some fizzy soda, which is the name of the game if my job is to make soda, I've got to pressurize that liquid with the carbon dioxide. I've got to drive that carbon dioxide into the liquid under the force of high pressure. So this makes sense. If I had a high pressure to force all the carbonation into the liquid, I'll get a high concentration of carbonation. So that makes total sense. This is an important result, and it's going to contrast with a liquid. Something in the liquid phase, where we're going to see that well, what are we going to see? Well, actually, what we're going to see is something different, and it's because I haven't really completed this properly. So this is true. Pressure is proportional to concentration, but what I want is the relationship between concentration and temperature. So it's not really equals. I want also. So if I look at the relationship between concentration and temperature, if I were to bring temperature to the other side of the equal sign, so to separate concentration and temperature on either side of the equal sign, I can see that concentration molarity is proportional to 1 over temperature. So there's an inverse relationship for pressure. Again, because they're a product on the same side of the equal sign, when one of them goes to the other side, it becomes a denominator, whereas the previous one was a numerator. So there's an inverse relationship. This is now going to contrast with a liquid, where we can see that concentration is proportional to temperature. So let's contrast this direct relationship with this indirect relationship. This is unusual. It's actually quite common. Well, it's common sense, but it wouldn't be predicted. I don't think it's a priori obvious. Let's see how we know this to be true, and we'll tap back into our discussion of dissolution at the molecular level. Think, for example, when you brew coffee or when you have to dissolve something. So whether it's coffee or you have to dissolve gravy granules into water, you can get a higher concentration of coffee or gravy granules, or it's easier to undergo the dissolution process typically with a higher temperature. So you increase the temperature, you increase the concentration. So this is definitely common sense from our experience with liquids. This comes out of the equation. It's also common sense from our experience with things like carbonation and soda drinks, for example. But there's a nice contrasting outcome that definitely would be worth remembering and thinking about. So I'm going to pause this video now, actually conclude this video, and think about this some more, as should you.